In section 6.4, we're going to talk about the central limit theorem, which is perhaps the most important theorem in all of probability. So let me kind of paraphrase this. There's a lot going on here. So what it's saying is, if we have any distribution, doesn't matter how it looks, normal or not, if we start getting samples of size n, and rather than looking at individual values, if we look at the average of that sample that we got, and we start plotting all of those averages, that's going to be the sampling distribution of the means. And so as we get larger and larger samples, as that increases, then that new sampling distribution of means will get closer to being a normal approximation. And the average of both the original and the new sampling distribution of means are going to be the means are going to be the same values, but the standard deviation of the new distribution is going to be the standard deviation divided by the square root of n. And so that's quite a bit to take in. Notice here our parameters that we're saying it's mu x, so still our mean, but the standard deviation is going to change to the standard deviation divided by the square root of n. And so let me go to this illustration here to try to elaborate on that again. Okay, so let's say we have any distribution. This is what the central limit theorem is telling us. So let's look at this distribution. Obviously, we know that is not normal. This one is actually skewed to the right. But the key thing is if it's normal or not normal. Not going to make a difference. What we're going to do is we're going to take some values from here. So we're going to just go ahead and take a small sample of 5 values. So say I take a value and it comes out here. Here's another one. Here's another. And then a couple more. And so that's what's illustrated down here. These are the 5 samples that I took from this original distribution. And rather than looking at individual samples, what I'm going to do is I'm going to calculate an average for these guys right here. So for these guys, I'm going to go ahead and calculate an average value. And that's going to be what I plot somewhere here. Okay. So I don't know what these numbers are. I'm going to go ahead and get some average. I'm going to get the average of them. And then I'm going to go ahead and plot that one single value right there. Now I'm going to keep doing this over and over. I'm going to go back and get another sample of 5, and I'm going to plot not those values, but the average of those values. And I'm going to keep doing that over and over. So a whole bunch of them. Okay, so I'm doing this over and over here. So this distribution on the bottom is now the sampling distribution of the means. So right here, this represents all of the averages of those samples of 5 that I got. And so what the central limit theorem tells us, I'm just going to put that there, I kind of paraphrase it for us, is what it's telling us is that this new distribution is going to be normally approximated. It's going to be approximately normal, despite that our original distribution is not normal. And that's, very, very strange. It's not intuitive that that's going to come out like that. And moreover, what it's going to tell us is that the means, so the mean of this distribution of the original one, here it's about 28. Well, the mean of this new distribution is going to be roughly about the same as about 28 or so. You could see to about 1 decimal of accuracy, they're about the same. So right there. And then furthermore, the standard deviation of the new distribution is not going to be the same, but if I get this value here and I divide it by the square root of n of the sample sizes that I'm selecting, that's going to end up giving us the standard deviation of the new distribution. So this is a very important tool because if we have a distribution that is not normal, well, here it gives us a way to kind of normalize it, so we could use our normal CDF function. Otherwise, we're not going to be able to calculate those probabilities. And so again, notice the subscripts, the mean of x bar here. So the mean of that, the new distribution, that's this one down here, we're saying is going to equal the mean of the original distribution. And notice here I'm using x, because those are the individual samples that we are actually taking there. So get a little bit familiar with the notation here. And this here, this mu sub x bar, is what we call the standard error. All right, so let's see this in practice. And so here we have an unknown distribution. So that's the key word there, unknown distribution here. We have a mean of 90, standard deviation of 15, and then we're taking sample sizes of 25 that are drawn randomly from the population. So notice that I'm not selecting one person, but I'm selecting groups of 25. So that's changing my axis here. I'm not calling it x, but now I'm calling it x bar. So these are sample means now. So right in the middle is going to be my mean here, because if you recall, the mean of the original distribution will be the mean of the sample distribution of the means. So they're going to have the same mean there. So that's mu sub x bar. And then my standard deviation is 15. But again, we're going to want the standard error. So that's going to be sigma divided by radical n, which is about 3 in this case, or it is 3. Okay, so that's our standard error. And so let's go ahead and sketch what we want. We're looking for the area between 85 and 92. And again, a key word here is it's talking about sample means here. So not individuals, but we're looking at the sample means. Okay. And here's our distribution. So notice again, I'm using x bar there, and then I'm changing that standard deviation to the standard error. So you want the probability, and again, I'm using x bar here. We want the probability that the means are between 85 and 92. And so we're going to use a normal CDF of our lower, upper. There's our mean, and then again the standard deviation, which we're using the standard error. Okay, so sigma sub x bar and then mu sub x bar as well. So how do we know to use the central limit theorem? Well, there's 3 giveaways. Okay, one is that it is not normal. Okay, so it said it was an unknown distribution there. The other one is that it gives you an n. So here we're selecting sample sizes of 25. In the last section, we weren't doing that. It wouldn't give you an n value. And then 3, it's going to say that sample mean. So we're looking at x bar in this case here. Okay, so those are going to be the 3 giveaways there. Now, for number 1 here, not normal, it could also be normal. That's fine. If it's a normal distribution, we could still use the central limit theorem, but that's a dead giveaway. If it's not normal, we're going to need to normalize it. Okay. So really the only difference here is that we're changing our standard deviation here, right? We're dividing it by the square root of n, and then we're being very cautious with our notation as well. Okay, let's try another one here. And so here a study was done about violence against the prostitutes. And so, and then post-traumatic stress that they developed. So they give us a sample here. The age range is 14 to 61. The mean age was 30.9, and then the standard deviation of 9 years. Okay. So let's look at A here, and we'll look at A and C for this example. So again, our distribution here, we're looking at X bar, and it's a giveaway because we're looking at a sample of 25. So we're not selecting one, but we're looking at a group of them. So that's going to be normal of 30.9, and then our standard deviation divided by the square root of n. Okay, so again, that's the standard error. And then if you recall, our average of the original distribution is going to be equal to the average of the new distribution of the means there. Okay, so here's our sketch. And again, we're talking averages, so I'm going to put X bar there. There's our mean in the middle, 30.9. And we're looking at what is the probability that the mean age of the prostitutes is less than 35. So there's 35, and we're shading less than. So we're going to go to the left. So there's our sketch. And so this is going to be a normal CDF. And again, since we keep going all the way towards the bottom, we want a very, very small number. So negative E9. There's our upper of 35, and then the mean, and then the standard error. So lower upper mu sub X bar, and then mu sub, and then sigma sub X bar. Okay. And so that's how we would input that into our calculator. Again, the key thing, noticing that we have a sample of 25 here to apply the central limit theorem. And then we're looking at the mean ages. So the mean age rather than an individual a person here. Let's look at part C, which is the 95th percentile. And so what we're looking for is the cutoff here that divides the bottom 95 and the top 5% there. And again, notice I'm putting X bar because we're looking at an average. So let me draw a little sketch here. So there's the cutoff for 95. Again, I'm looking for that X bar, that average age. There's 30.9, our mean in the center. And then our sample size here, we're getting samples of 65. So I'm going to make a note of that and keep track of that here. So the inverse norm, again, area to the left, our mean, then our standard error here. There we go. So that's going to give us about 32.74, and that's how we input it into the calculator. And then just to be correct here, this distribution here would be 30.9, and then we would have 9 over square root of 65. And we're talking means. There we go. And what it wants us to do is to interpret this. So this indicates that 95% of our subjects here in the sample of 65 are younger than 32.7 years on average. So that's going to be the cutoff for that 95 percentile.